Hi there. Today we're going to continue with On the Measure of Intelligence by François Chollet. Now, if you remember last time, if you haven't seen last time, go watch part 1 if you're interested. This is a multi-part series on this paper. Why? Because the paper itself is very long. It's 40 pages, the main part, and it's a big wall of text. So I've opted to basically pull out notes and show you the notes that I have pulled out, and to divide this into multiple parts. So last time we went over sort of the history of assessing intelligence and the basics. And I know I said this time I'm going to get into the math, but I lied. So I realized that there's still a lot that comes up in part 2 of the paper before we get into the actual math. So this part is going to be about the prerequisites to that, and then next time math. I'm sorry to disappoint anyone. Yeah, you might just skip this one if you want. I do have to shout out Tim Scarf, who, of course, runs the Machine Learning Street Talk channel podcast with me and Connor Shorten together. Tim has just made an entire video about this paper, about On the Measure of Intelligence, and his videos are usually like super high quality, like higher than mine, and it's the entire paper. So if you want to, know the end of the story, or, have a different take on the paper, definitely can recommend his video. I do make a guest appearance there. So yeah, that's a given. And I will still finish the paper on this channel, just in this style right here. So all the options are available to you. Let's dive into part 2. So if you remember part 1, we sort of went over what it means to be intelligent, and we differentiated basically 2 things, which are skills and abilities. So a skill is how well you achieve a given task, or how well you can do in a given task. So this could be chess, or Go, or something very, very measurable. An IQ test is a specific task. So these things right here, they're all tasks. But these tasks aren't the thing we're interested in. Just because a machine is good at chess doesn't mean it's intelligent. What we want is sort of a generalizable skill. So we want to assess how generalizable is an ability. So can I throw a computer at a new problem that it has never seen before, and it can solve that? And that's going to be this generalizability, this notion of, can you solve things that you have never encountered before and weren't prepared for? That is going to be the basis for us to measure intelligence. So Chollet says you have to optimize directly for generality and flexibility rather than task performance if you want to build an intelligent agent, right? You have to sort of build something that is not just good at a thing, it is good at getting good at things. That's almost a quote-worthy thing. So if you just give it a single task, it says that the learner will just take any available shortcut. So if you just say you have to be good at chess, the developer of a system can exploit all the tricks that make you good at chess, and you don't have to be smart. You just know, basically, if you had enough memory, you could just memorize all the moves of all the chess games ever. Okay, that's why we say hard-coded chatbots are not intelligent. So hard-coded chatbots, they simply match your input to a database of regexes, and then they answer. And we're not very impressed, because as soon as I give them something that is not covered by their regexes, they fail. They just say, I don't know, or something like this. In fact, what is intelligent is the engineer in that case. So the engineer that makes the program is intelligent. So he has this drawing, I think I've shown it last time, where you have the environment, and there is this agent. And if the agent is really good with the environment, you might consider that intelligent, but in Chollet's mind, you have to also consider here the developer of the agent. It could be that the developer is very intelligent and just builds the agent to interact with the environment in a manner that it gets a lot of reward. It's very good at a skill, but the agent itself might not be intelligent. So it says the intelligence of a process is not encoded by the performance of a system, but by the fact that the same process can be applied to different tasks. So in this case, if I have a new task, a new environment, so E2 right here, the question is, could I throw the same agent at that, even if it hasn't seen it before? Or would I be able to take the same developer that develops me a new agent, agent 2, that then can solve the task? In the case where I can throw over the agent, that would make an argument that the agent is intelligent. But if I can't, you'd have to make the argument that the developer is the intelligent part here, which of course is the point of what he's saying right here. So hard-coded programs themselves are not intelligent, but, and this is the case, the same counts for adding more training data. So not only is the hard coding not intelligent, it's also, Chollet says, not intelligent if you simply add more training data. So a machine learning system that sort of learns to how to interact with these environments. If you can imagine that you have lots of environment, and so on, that give you a dense sampling of the environment space, right? So you have all of these environments, you build all of them, and you train this agent to interact well with all of them. So you give it lots of compute, lots of data, and the environments are really a dense sampling of the environment space. It will be able, even though it has never seen environment 2, right, this environment right here, it might be just able to generalize to this environment, given that it has been trained on all the environments here, like it has been trained on every possible environment around this environment that is similar to this environment. It could generalize to environment 2, but also we wouldn't view that as intelligent because it in a sense, this skill has been bought with data. And this notion of buying skill comes up a lot in this paper. So Chollet says there are two ways to buy a skill. And by buying, he basically means you don't buying as opposed to intelligently solving the skill. So whenever you buy a skill, that's not intelligence, Chollet says. And you can buy a skill by either hard coding the solution or giving lots of data. And there is like this spectrum where you completely hard code a solution. And here is where you completely only feed data. So here would be something like GPT-3, right? There are almost no priors there. It's just a transformer, big transformer, and you just throw in data. Lots and lots and lots and lots and lots of data. So in this measure, last time I've had lots of people, when GPT-3 came out, I've had people commenting on the part 1 of this paper saying, isn't GPT-3 intelligent because, it can sort of generalize to these tasks that it hasn't been trained on. By the way, if you haven't seen the GPT-3 video, you should go watch it. Something tells me this video is popular. It might be the 5 times as many views as any other video. So at least it's not a terrible video. So, but in essence, GPT-3 can solve these tasks that it wasn't trained for, right? And therefore, you might argue in this definition right here, it could be intelligent because it can generalize. But there is this counteraction where Chollet says, maybe you have just bought that skill with lots and lots of data. Now, I actually don't know what to say to this because, it really seems like GPT-3 generalizes to tasks it has never seen before, but also it has had a lot of data. And so as of right now, it is not really clear where the line is here. Like when are we going to argue that GPT-3 is actually, like it could be that it has had lots of data, but also it is intelligent. How are we going to make that distinction? And I guess we're going to get into the math part, but I can tell you right now, the math part is so abstract as it is not really practical. It is like a theoretical framework that you might be able to approximate, but there is like a wishy-washy thing going on. But he basically says, okay, there's this spectrum of hard coding, over here, and then fully learning from data, and with all of these methods, and in between methods, like a CNN would be here because it has like considerable priors because of its architecture and so on. And over here would be something like an A-star search with like a learned heuristic or things like this. You can get good with any of these things, but the intelligence is orthogonal to that. So orthogonal to that is the intelligence axis. It has nothing, Cholet says this has nothing to do with this dimension. You can buy skill with this, but it's basically like, it's like a triangle, almost sort of, where you have hard coding, data, and then intelligence. And it's like its own axis. So the hard coding refers to the priors of a system that the developer has basically built in. And the learning from data refers to its experience. So basically, the more experience a system has had, the more it can generalize to a new skill. That doesn't mean it's intelligent, it just means it had more experience, or respectively, more priors. So the example he gives, a locality-sensitive hashing, which is basically like a nearest neighbor method with enough data can solve any task, right? Like nearest neighbor, enough data can solve any task. That's, I think it's a famous theorem that establishes that. So keep that in mind. That is why we basically need to pay attention to how much data went into this algorithm and sort of subtract that from our notion of how intelligent it is. Yeah, that's what he says. When we measure intelligence via skill, and this is really the only thing we can measure, we can only measure how good an agent is at a given skill. Anything higher than that, we can't measure. So we must measure a skill, but we should factor out priors and experience. And that's going to come up later, we should also pay attention to generalization difficulty. So generally, how difficult is the task to solve given the experience we had? Because if the task is more difficult in a generalization sense, so if it's harder to, from what we know, get to the point where we can solve the task, then that would display higher intelligence. Yeah, it says solving tasks via experience and priors has nothing to do with intelligence. It's just more experience, more priors. So goes back to human intelligence. He says how universal is actually human intelligence, and he gets to the point where he says it's not very universal, because first of all, there's no free lunch theorem where it says any two optimization algorithms will perform the same if you integrate across all possible problems. So it's even questionable whether something like general intelligence could even, like universal intelligence, could even exist. But if we look at the G factor, which is used sometimes to assess human intelligence, or is the measure for human intelligence that is established right now, then they only encompass tasks that humans can perform and understand, of course. And I would say they only encompass tasks where humans actually differ with respect to each other, because if you're making these tests and you have a human for 40 minutes or so, you're not going to give the humans tasks where they don't differentiate from one another. So it's going to be a range, like a very, very small subset of tasks that are exactly hard enough such that a couple of humans can solve them, a couple of humans can't solve them. They're going to be, understandable by humans, and understandable ideally by any human. You don't have to have special pre-knowledge, not have studied biology in order to answer the questions, or not, have a higher degree in math or something. So the reference for the G factor is very much a reference frame of human values. And he compares this to physical fitness. So if we call someone physically fit, what do we mean? We mean this general abstract concept, right, of physical fitness, where it's not really one skill. So you can measure humans in how fast they run, how high they jump, how fast they swim, and so on, and how much they can lift, And across that, you'll find generally that all of these things correlate, and the result we call physical fitness. But it's not like physical fitness is a universal measure. So we only measure humans at tasks that humans can solve and are different at. So the physical fitness is very human-centric, and so is intelligence. So that's the analogy. I think it's a very good one. He gives this example where humans are, for example, very, very good at shortest path traveling salesman problems, give up to a certain number of nodes in the graph. Humans can solve them extremely well to like very good degree. But as soon as you go to longest path problem, which shouldn't be that much harder if you just look at it from an algorithmic perspective, but humans are terrible at it, absolutely terrible. And that probably has to do with the fact that we have a prior, and the prior is much, much more adapt to shortest path problems than longest path problems, because in our history, in our evolutionary history, it made a lot of sense to build in a navigational unit in the brain that calculates shortest routings. But it's probably like your fitness is not very much affected by you being able to calculate the longest path, unless you want to really avoid something. And just I don't know, you don't really want to walk in these shoes. So that should be taken into effect, and it shows that intelligence is a very human-centric concept. So when we talk about general artificial intelligence, what we mean is it's tied to a scope of problems, and that's going to be important, that we can only measure intelligence in this framework with respect to a scope of problems, and the scope that we consider is the human scope. So why human-centric? Because we must have a scope, and the human scope is the only meaningful scope. It's the only one we know. That, there's one thing in the universe that we think is intelligent, that we know of, and that's humans. And or to a degree, like one can make the argument it's general biological life on Earth, but we measure intelligence with a human scope intelligence test, and that's the thing we have. We don't have anything else. So, yeah. So we ask ourselves, what are priors of humans? What has evolution built into humans? And Chollet decides on 3 levels of priors. The low-level priors, which are like reflexes. So if I pinch you flick. Like if I flick you move back, and if I shine a bright light at your eyes, you close them, and so on. So this, Chollet says, is not very interesting because that's, let's say, nothing to do, like we feel that it has nothing to do with intelligence. Okay. And then there are, I'm going to skip this one, say there are knowledge priors. So the knowledge priors are, things like the fact that there are objects in this world. That's a knowledge prior that the human have. That's built into you. The notion that the world consists of objects, and you can interact with these objects, right? The navigation capability. We say, okay, navigate there. Humans can do it very, very well, as I already said. They're very good at shortest path problems and so on, intuitive navigation. That's built into you by evolution. That's a prior. Goal-directedness. Humans generally view the world in terms of agents, and in terms of agents having a goal, like chasing after something. He makes this example. And if we observe something, we often want to frame it in terms of agents that pursue goals. And as soon as we can do that, that allows us to some degree to predict the world. And that's probably why this evolved. So very valuable skill. Social intuition and things like counting, like basic arithmetic, are built into humans. And Chollet says, if we measure intelligence, this is what we must account for. Okay, so these things should not count towards intelligence because they're already built into humans if we measure human intelligence. So you wouldn't test human intelligence by making them count, because that's built into the humans. Now, the third kind of priors that humans have are meta-learning priors. And the meta-learning priors is basically your ability to learn something. Okay, this is your meta-learning prior, is just your ability to learn something that is not learned. No one has to teach you how to learn something. I guess there are like learning strategies and so on, but you as a human are incredibly good at picking up new skills. And the skill of picking up new skills, that's built into you. Among these are assumptions that the world is a hierarchical and causal place. That's how you see the world. And because you see the world like this, you can pick up these new skills very, very quickly. You can through explaining the world, you can pick up new skills. And that is usually what we mean by intelligence. If someone sees a new unencountered before situation, thinks about it, which basically interprets the world in the hierarchical and causal way, and then is able to come up with a skill that solves the problem. And we generally view that as intelligence. So if we want to measure intelligence, we should measure this, basically how good you are at picking up new skills, while accounting for these things, okay, when we compare to humans. So Chollet says tests of intelligence should be founded on human-like knowledge priors. And it basically makes the case that these should, if we build machines and compare them to humans in, let's say, in terms of intelligence, we should build into the machines these things right here. These we should give them. Like we should give them a counting module that they can use, like a calculator app. We should just build that in and make that available for the agent to use, like basic arithmetic. You shouldn't have to learn this. We should build in the notion that there are objects. We should build in the basic navigation module and so on that the agent can use. You can almost think of it like, there's whatever your reinforcement learning agent, A. It consists of like this big neural network with lots of layers, but then each layer maybe has access to, the calculator app right here. And each layer has access to maybe also memory. I would guess memory is one of those priors as well. Or, it has access to a navigation prior. Let's draw a little world map right here. This is Google Maps. It can do that. It can query that sort of. And we shouldn't, if we want to build something that's intelligent as compared to humans, we should build in the navigation. We shouldn't, at least as much as human can do it. I mean, it's cool to have a machine learning system learn navigation, but that makes it less comparable. So it says either we should match the humans or we should account for the difference. So we should kind of let the difference be let the difference between the humans and the machines into the measure of the intelligence. Further, if you test intelligence, all of these priors should be explicitly described and not rely on additional priors. So that's often the case in IQ tests. There are so many priors that are not explicitly described because we just think, every human can count. We don't need to write down that our prior assumptions are that the human can count or understand language. And that's, I hear, sometimes a problem in IQ tests that basically the better you understand language, the better you score at these tests. And therefore, the tests are more like a measure of language ability than intelligence. So this is much informed by, so I think the psychometrics community is on the same path right here. He goes into this theory of human core knowledge where he basically expands on what the human priors are. So this core knowledge theory takes 4 takes on 4 different categories. So the first one is object-nascent elementary physics, which means you as a human have an inherent knowledge that there are objects, as I said, but also of elementary physics, that stuff sticks together, persistence of objects. And some people say, this is learned. So young children, they do not know object persistence, and that's why peekaboo is so interesting. But because they think you're gone, right? They think, if a parent goes to the toilet, they really think the parent doesn't exist anymore, and only later they learn object persistence. But I would question whether or not that's actually a learned thing or simply a built-in module that gets switched on at that particular point, because probably evolution deems it not necessary to waste resources on that module before that. So I would be cautionary saying that object persistence and all of these things, in fact, are learned. I would argue more that they are built in and are simply switched on at a given time during development. Because we also know these things, like object persistence, I think you can almost pinpoint the month of a human's life when that's switched on. That will be so accurate. And if this is really learned, then you'd have to assume like a very regular structure of the training data distribution that a baby gets to experience. So I'm not sure here, but it's not my opinion, it's Cholet's. Contact interaction, the fact that you can interact with objects by contacting them, or that objects can interact with each other by being next to each other, that's built into you as well. You don't have to learn that. If you compare this to like an RL agent that has to learn all of this from pixels, basically, you can see why Cholet has a problem with the current direction of deep learning and claiming that things are intelligent there, because the comparison is just very invalid. So the second core knowledge you have is agentness and goal-directedness, and we have already discussed that. Then natural numbers and elementary arithmetic. Small numbers you can add, subtract, compare, sort, that sort of thing. And elementary geometry and topology, where in there would be orientation and navigation, and then distance orientation, if it's something is inside or outside of in a room, and so on. Now, I have heard, and this might be a myth, that there are languages where left and right, like relative directions, have no meaning, like doesn't exist in the language, but they always use absolute directions, and then these people automatically like have a much better orientation at all time. Like if they get into a building, they can always tell you where north is. That's a myth, but I would guess that's pretty cool, and just shows you the flexibility of something like orientation. Sure, we can all orient, but it seems like by simply learning a different language, you can sort of supercharge that drive for orientation. So again, it sort of feels like there is a lot of nature versus nurture going on in here, in that all of these things, yes, you probably have a tendency built in to learn objectness and physics and so on, but then also probably a lot of it might be learned in addition, or you might just be able to supercharge one of these modules that's inside of you. I think there's lots of room for discussion here. So he says tests for intelligence should only involve core knowledge, and the AI systems taking these tests should hard code that core knowledge. So basically what he said before, we should build in these things right here, these core knowledge things. We should build these into the AI systems if we want to compare them to humans. Because if they have these things and only these things built in, then they sort of have the same starting point as a human. Now, in this case, this is where I sort of disagree, because like the notion that we can ever explicitly list the priors that humans have, to me seems a bit ridiculous. So I guess we can sort of approximate this, at first, but we will never exhaustively exactly describe what the priors are, what is learned. We've seen this with the orientation, like how much of that is learned and prior. And then secondly, even if we could list them pretty exactly, what says that we can exactly program them into an agent such that it can make use of it? Like that's an even harder challenge. So I'm not so sure that this AI systems should hard code core knowledge. He's going to try that with this ARC challenge that we're going to look at in like the last part of this series. But and it's a cool test for intelligence, I admit that, but I doubt that anyone really manages to hard code the core knowledge. And he says tests should only involve core knowledge, and we're going to see how valid that claim is for his own ARC challenge. Now, luckily in the math part that's going to come up, he doesn't strictly rely on these things. So he gives us a way how we can compare, even if the priors of two systems are different, we can compare which one's more intelligent. All right, so that was part 2 of this series. It's already been a while now, and this is only part 2, and I do promise next time we're going to get into the math. I hope you liked this, and go check out Tim Scarve's video on the same topic. As I said, usually much higher quality videos than mine, and I'll see you next time. Bye-bye.